What I like about this question is it doesn't require a lot of A-level knowledge to understand what's being asked, but it does require A-level knowledge to be able to answer it. We've got a square, side length's 1 centimeter. I'm just going to label them as 1. And then one corner is O, so without loss of generality, I'm going to make it the bottom left. And then we're placing P and Q somewhere either inside the boundary or on the edge. And we want to show that the length of at least one of the lines, when we basically make a triangle out of them, must be less than or equal to root 6 minus root 2. The first thing I thought to do, and I'm going to do it here, is what if we just make a triangle like this? Would that one work? It seems like a good, like quite a large triangle. Of course, if you make a triangle like down here, then that's going to be a really small triangle. We want to we want to show that at least one is less than or equal to this. So it kind of makes sense to maximize the length and actually, I think I'll say it now. We're trying to find the maximum value of the minimum out of OP, OQ, and PQ. But let me just get back to this triangle that I've drawn then. Okay, here the minimum value out of PQ, PO, and OQ would be 1. Actually, both of these would be 1. This one would be root 2. So let's just find out, is that bigger than root 6 minus root 2? Well, what we can do, rather than comparing the numbers, is compare their squares. This is a nice way to compare numbers, especially when they're involving square roots. So we're going to get 6 plus 2 minus 2 lots of root 6 root 2, which is root 12, which becomes 8 minus, now that is root 4, so it's going to be root 48. And if I'm minusing root 48, that is going to give me a bigger number than if I minus root 49. If I subtracted a larger number. And the reason I've done that is that this is just 1, because it's 8 minus 7. So I've just shown that the square of root 6 minus root 2 is bigger than 1. In fact, it's not going to be much bigger, because that root 48 is going to be very close to root 49, and I've squared it. So therefore, root 6 minus root 2 itself is bigger than 1. So condition satisfied for triangle shown. Right, now next bit, it did say that the points can be within the square, but it doesn't make any sense to put them within the square. If we put them here and here, then we're going to get a smaller, large, a smaller, smallest length than if we extended the triangle further and then joined it. So place P and Q on the boundary to maximize the smallest length of the triangle. Hopefully, I could say if they're inside, then extend. I could illustrate a process how you would do it. We could just extend along the same line until we hit the boundary. But equivalently, we can just say, just place them on the boundary. What I'd decide to do at this point then is split it into some different cases. It feels like it's going to look a bit like the triangle that I've shaded, but I just want to kind of consider some different situations. Case 1, if P and or Q, no, let's say they're both, P and Q, actually, sorry, P or Q, or both, um, lie on, and now I'm going to label, actually, I'm going to label the corner A, B, and C. So if P or Q lie on OA or OC, then the condition will definitely be satisfied because our minimum length would be less than or equal to 1. Because I showed when it's in the corners that it's going to be 1, and that is less than root 6 minus root 2. So I don't need to consider that anymore. Also, if they're on the same, so if they were both on PQ, for example, like this, then PQ is now going to definitely be less than 1. So case 2, P and Q are on AB or BC. Now, PQ would be less than or equal to 1, and the condition would be satisfied. So this leaves us with case 3. Without loss of generality, P is going to be on AB and Q is going to be on BC. They're going to be on these opposite corners. Sorry, I meant so not opposite, you know what I mean? It needs to be on AB and BC. That's the only case we've not looked into. Okay, before I move on then, I just want to talk about the background work. What we're actually trying to find, and this is absolutely crucial, is the maximum value of the minimum out of OP, OQ, and PQ. We did an example. We've shown that that doesn't work. I've then just explained why they have to be on the edge to find this maximum value. Doesn't make any sense to have them in the inside. And then they have to be on A, B, and BC to find this maximum value. If they're in the other situations, then the condition will definitely be satisfied because we get a minimum length that is less than or equal to 1. Okay, so it kind of makes sense anyway to have it say here and then maybe here. But that length is looking quite a lot shorter. So actually, I want to adjust it and I want to make that one longer, don't I? So if I draw it something like that, then that seems to be longer. And when I was doing this and playing around with it, I just thought I need an equilateral triangle. Because if we don't have an equilateral triangle, if you draw something like that, we can make these lengths really large, brilliant, but we want to maximize that. And then to make that larger, we'll make the other one smaller. And it's going to be the point when they all have the same length that gives us our maximum minimum value. I think it takes a bit of time to get your head around this. So yeah, I just keep when you say it's the maximum minimum value, we're trying to find the minimum value out of OP, OQ, and PQ and show that it's got to be less than or equal to root 6 minus root 2. So there's so many triangles where that will immediately be true, but we're trying to find the one where it would have the largest possible value for either OP, well, largest possible value for the minimum of OP, OQ, and PQ. That's what we're trying to find. And so the equilateral triangle is going to give us this. I kind of just justified that to myself and then solved it, but I'm going to go into a little bit more detail now. I saw somebody else's solution and it did work really well. So what we can do is I'll call this P and this Q. Consider the sine rule. So here we're going to have sine P over P is equal to sine Q over Q. Now the sine rule implies that smaller angles, I don't want to say smaller angles. No, that does actually make sense. Smaller angles are opposite shorter sides. So if you had, say, 30 degrees, 50 degrees, and 100 degrees, then the shortest side would be opposite the 30. The reason being is that sine 30 is smaller than sine 50 and sine 100, so we're going to need to divide by a smaller amount to make it work. You could also cross multiply a pair and see that sine q times sine p is p times sine q, and since if this one is smaller than this one, then we'd have to have this one smaller than this one. So it all goes together. So that is a mathematical fact, and it's worth being aware of. I've seen maths challenge questions where it kind of seems intuitive, I guess, and if you start drawing a triangle, but yeah, it's not really something that I thought about a lot, but it's going to be useful here. So we've got that P plus Q plus O, the angles that is going to be 180. So to maximize the shortest side, which is what we're trying to do, we must maximize the smallest angle. And therefore, we must make them all 60 degrees. Because if you made one like 70 and 160 and 150, well, 50 is going to be opposite the smallest side. And that side will end up being less than if you had maximized the angle and hence maximized the side. So we're pretty much ready to do the calculation. I've got O, okay, I've got A, B, and C. I've just put them on as well. And then I'm trying to make an equilateral triangle. So 60 degrees, 60 degrees, and 60 degrees. Now what this means, remember I've got a length here of 1. Now this green triangle and this purple triangle, they must be congruent because they have the same hypotenuse, because remember it's an equilateral triangle, and they have the same side here, and they have a right angle. So RHS, congruent triangles, they must be the same. And that means that we can split the remaining 30 degrees into 2 here and get 15. And then this here will be what is left over, 75. In fact, I'm not going to label that 75. Up here we then get 45 and 45 again. This length must be the same. There's going to be a line of symmetry going along the diagonal. So let's focus on this green triangle. Actually, we can just look at this in isolation. It's got 15 degrees here. We've got 1 here. We just need to work out what the hypotenuse is, capital H. So cos 15 is going to be 1 over H, which means H is going to be 1 over cos 15. We just need to know the exact value of cos 15. And we can use addition formulae for this. So this is finally where the second year level maths is coming in. Okay, cos 15 is actually going to equal cos 60 minus 45. We know our exact values of cos 60 and cos 45. So cos A minus B is identical to cos A cos B plus sine A sine B. So this is going to be cos 60 cos 45 plus sine 60 sine 45. Cos 60 is a half. I'm not going to go into details on remembering these. Okay, I've got plenty of other videos on this. And you can derive them as well if you forget them. Cos 45 is 1 over root 2. And then sine 60 is root 3 over 2. And sine 45 is 1 over root 2. So we get root 3 plus 1 over 2 root 2. And therefore, h is just going to be the reciprocal of this, 2 root 2 over root 3 plus 1. And I can rationalize the denominator. I'm trying to show that this is root 6 minus root 2. We're very, very close. So I'm going to get 2 root 6 minus 2 root 2 all over 3 minus 1. The 2's are going to cancel, leaving us root 6 minus root 2. So this is the maximum of the minimum of OP, OQ, PQ. Therefore, for any P and Q, 1, or at least 1, at least 1 of OP, PQ, OQ must be less than or equal to this value. That is what we've shown by finding the maximum possible smallest length. Okay, quite an explainy question here. I've just tried to justify every step. I hope it's making sense. It's quite nice how, well, you have to do this. I feel like you should do this justifying, but at the end of the day, it turns into an addition formula problem once you've realized it's an equilateral triangle, and it actually works out really quickly from there. So you can do it obviously quite quickly if you spot that. I just feel like you should justify all your steps, like why it should be on the boundary, why it should be on two sides, this one and this one, why it should be an equilateral triangle. You can justify symmetry, potentially. That's kind of how I did it in my head. I just thought surely that's going to be the case. Or you can use the sine rule and say that smaller sides are opposite smaller angles are opposite shorter sides. So we need to get the to maximize the shorter side, we should maximize the smallest angle and then follow through the maths on there. Anyway, well done.